It's my pleasure to introduce the next speaker, Carlos Kenig from the University of Chicago, and he will speak about the energy critical wave equation. Carlos.
Okay, thank you. Can you hear me? Okay. Okay, thank you. So first let me thank the organizers for giving me this opportunity to be here today to celebrate Sergiu's accomplishments and his birthday. I have known Sergiu for a very long time, not as long as Peter, but still quite a long time. I first heard of Sergiu, I think Sergiu and I graduated the same year. And I think I first heard of Sergiu in a series of lectures that Louis Nierenberg was giving at the Institute for Advanced Studies when I was an instructor at Princeton. I think this was 1979. And one of Nierenberg's lectures was to explain the breakthrough work in Sergiu's thesis on the long-time existence solutions to hyperbolic nonlinear problems. So I just want to say that I have great admiration for Sergiu's work. I think it has played a transformative role in nonlinear hyperbolic equations and in the mathematical theory of relativity. I also want to say that there's another aspect of Sergiu's labor that I have great admiration for, and that's the fact that he has an uncanny talent to detect very young, promising researchers and attract them to his programs. And they then develop and become great forces in the field. And I think this has been an incredible contribution of Sergiu's to our field. So thank you, Sergiu, and happy birthday. Okay, so today I'm talking about the energy critical wave equation. And I'm certainly not an expert on hyperbolic PDE. So maybe I should explain a little bit of how I came to this position. About 12 years ago, Frank Merle and I developed a method to attack the problems of long-time behavior of solutions to critical dispersive problems. And we call this the concentration compactness rigidity theorem method. And I guess our final goal in this method was to see if we could at least find one example where we could understand the long-time asymptotics of solutions without any size restrictions. And in working on this method, we came to the energy critical wave equation, and slowly we started making progress in that and realizing that this was maybe a good candidate for this project. Okay? So let me now be more specific and go to the details. So in studying the long-time asymptotics of wave equations and dispersive equations, there's been a widely held belief in various communities that coherent structures describe the long-time asymptotics of general solutions to nonlinear hyperbolic and dispersive equations. And this belief has come to be known as the Soliton resolution conjecture. So notice that I say belief when I refer to a conjecture. So that's because it's more than a conjecture, it's a series of beliefs. Okay. Can you still hear me when I look up? Okay. So this, the Soliton resolution conjecture has been one of the grand challenges in partial differential equations. And loosely speaking, the conjecture says that the long time evolution of a general solution of most hyperbolic and dispersive equations asymptotically in time decouple, these solutions decouple into a sum of modulated solitons, which are traveling wave solutions, and a free radiation term, which is a linear solution, and this free radiation term disperses to zero. So this is a very beautiful conjecture in my view, which postulates a simplification. So this is a very important concept here. There's a simplification where you have some very complicated dynamics of this possibly large solutions to nonlinear dispersive or hyperbolic equations. And in the end, asymptotically, you can decompose these dynamics into a superposition of simple nonlinear objects, and these are the traveling wave solutions, and a linear object, which we can understand by Fourier methods. Okay? So until very recently, the only cases in which such asymptotics had been proved was for integrable equations. Integrable equations are equations that reduce the nonlinear, where the nonlinear problem gets reduced to a collection of linear problems, or in perturbative regimes. So in 2012, 2013, with Ducaer and Merle, we established this desired asymptotic decomposition for radial solutions of the energy critical wave equation in 3 space dimensions. And this was the first case, to our knowledge, in a Hamiltonian situation, you can get such a, oh, I'm sorry. That you can do such a thing. And the first result was for a well-chosen sequence of times, and the second result was a proof of this for a general sequence of times. So let me now write the equation. So this is the concrete equation. This is the wave equation here, and then a semi-linear power, which is well chosen so that the equation is energy critical. And we are x in Rn and t in I. And also notice that we have the sign minus here, which is the opposite of minus the Laplacian. So that there's competition between the linear and the nonlinear terms, and that's what we call focusing. Okay. And the initial values are in the homogeneous ovalid space H1, that is to say have one derivative in L2, and the time derivative are in L2. And this is for n3, 4, 5, 6, and so on. I is a time interval, and since we're looking at the Cauchy problem, let's say that 0 belongs to the interval. Now, it's been known for a long time that small data yield global solutions, which scatter, and I'll explain what scatter means in a minute, while for large data, we don't know if they will exist globally or not, but at least for a maximal interval of existence, we have a solution which is continuous in the energy norm, and it has this additional regularity property. So it's a space-time norm is controlled. Okay. Now this energy norm is critical, and what do I mean by that? It's critical for the scaling. So if we take a solution u of xt, and we consider u lambda to be the scaled version of the solution, where we scale space and time equally because we are hyperbolic, and this is the correct factor, then this is also a solution, and the H1 norm is preserved for the original, for the H1 cross L2 norm is preserved for the initial data. So, as I was saying, this equation is focusing, and here we see that reflected in the conserved energy, which first has the standard energy for the wave equation, and then has the contribution of the nonlinear term, and we see that there's a minus sign so that the energy can be negative. Okay? So let me just say that the case of the defocusing equation, where you change the sign of the nonlinearity and then you change the sign in the energy and now you have a plus, was extensively studied in the 80s, 90s, up to the 2000s. And one can summarize these results by saying that for large data or arbitrary data in H1 cross L2, the solution exists globally and behaves asymptotically as a linear solution. That is to say, scatters. So this is the summary of a great body of work. People who have contributed here have been Grilakis, Shatta-Struve, Kapitansky, Bahuri and Shatta, and Bahuri and Girard, and so on. And so there's a great body of work in that, but the conclusion is that the asymptotics is the asymptotics of the linear equation. So now we're going to try to understand the case when the sign is the opposite one. So the first thing that happens here is that we can construct solutions which blow up in finite time. And that's very easy by considering the ODE. So you just forget about the Laplacian, you look at the corresponding ODE, and you find the solution. So in the three-dimensional case, you can take by word 1 minus t to the minus a half is a solution. Solves the ODE. Okay? And now once you have a solution like that, you can cut it up by using finite speed of propagation. What's that mean? No, I don't think this controls that. Anyway, so it is easy to use finite speed of propagation to construct solutions which cease to exist at time 1 and the norm tends to infinity. Okay? So this is, and we call this type 1 blowup. Now the interesting thing here is that there also are type 2 blow-up solutions. Those are solutions for which the final time is finite, but the norm remains bounded as we approach the final time. And the breakdown occurs here because of concentration phenomena. The gradient squared is concentrating like a delta mass as we approach the final time. Okay? And the fact that such solutions exist is a typical feature of energy critical problems. The first example of such radial solutions were constructed in the three-dimensional case by Krieger, Schlag, and Tataru, with some refinements later on by Krieger and Schlag. And then in the four-dimensional case, there was a different construction by Hilaire and Raphael. And recently, Jacek Jędrzej has found still another version, another construction in the five-dimensional case. So, if you think about what Soliton resolution says, this can only be expected for type 2 solutions because the Soliton resolution implies the boundedness of the H1 cross L2 norm. So, the question is there a Soliton resolution for a type 2, what we call type 2 solutions, that is solutions for which the norm doesn't blow up. And the final time of existence might be either finite or infinite. Okay. So let me just give some examples of type 2 solutions. Let's say we saw when t plus is finite, some type 2 solutions. When t plus is infinite, these are the small solutions, for example, the scattering solutions. That is to say, a solution such that as you evolve to infinity, the solution looks more and more like the linear solution, the associated linear equation, with some other data. So small solutions are scattering solutions, for example. Okay? But there are other examples, many other examples. For example, if you forget now about the time, instead of forgetting about the Laplacian, you end up with a well-known elliptic equation. So this is a well-known semi-linear elliptic equation which played a very important role in the solution of the Yamave problem in geometry. Okay, so this was a very well-studied equation. And let me say that I will call Q, it belongs to sigma. This will be a code for Q is non-zero and solves this elliptic equation. Okay. So there's another well-known example here of solutions to this elliptic equation. This is W of x, 1 plus x squared over n times n minus 2 raised to the minus n over 2 power. And this is a solution of the elliptic equation, as you can check by differentiation. And of course, this is a stationary solution of the hyperbolic problem. And as such, it doesn't scatter, because solutions that scatter it's very simple to show that if you integrate the gradient on a unit-size box, as you go to infinity, that has to tend to 0. But of course, for a static solution, this is constant, so they do not scatter. Now, this particular solution to the elliptic equation has several important characterizations. First, up to sign and scaling is the only radial non-zero solution. And this is due to a combination of work of Bohojaev, Guy-Dasny-Nirenberg, and Kwon. And the work of Guy-Dasny and Nirenberg shows also that up to translation and scaling, it is the only non-negative solution. Okay. However, there's a continuum of variable sign non-radial solutions. And these were not studied so much by people interested in geometric problems, because in geometric problems the non-negative solutions were the ones of main importance. And the first person, to my knowledge, to construct such solutions was Ding in 1986. And he did this in a functional analytical manner. And then more recently, Del Pino, Musso, Paccard, and Pistoia have made much more explicit constructions that one can examine with the naked eye. Now, there's also There's a further characterization of this W due to Talenti. In fact, probably this goes back to Bliss in the very early 20th century, saying that W has this characterization as the extremizer in the Sobolev embedding, the natural Sobolev embedding, where C sub n denotes the best constant in the Sobolev embedding. And because of this variational characterization of W, we call it the ground state. Okay? The solution with the least energy of the elliptic equation. So, as I mentioned at the beginning, with Merle, we in 2008, we proved the following ground state conjecture. It says that if U is a solution whose energy is below the energy of W, there is a dichotomy. If the gradient is smaller than the gradient of W, then you have global existence in both time directions and scattering in both time directions. And by the way, this number is an explicit number that one can compute. It's a known number. It can be expressed in terms of gamma functions. Now, the other case is when the opposite inequality holds, and in that case, there must be breakdown in both time directions. And finally, you will ask me what happens with the case of equality. And it turns out that under this condition, variational considerations show that there is no such function. Okay? So this completely analyzes the situation below the energy of the ground state. And that's why we call this the ground state conjecture. Now there is a threshold case when you allow for equality here, and this was completely described in work by Ducayer and Merle. This was a very important work which also introduced some further technical tools into the subject, and which uncovered also two other important solutions here that I won't have the time to talk about today. So this ground state conjecture was proved through the concentration compactness rigidity method, which we introduced for this purpose, and this has become sort of a standard tool to understand the global in-time behavior of solutions below the ground state threshold for critical dispersive problems. Now, what are the traveling wave solutions for the energy critical nonlinear wave equation? Well, these are obtained as Lorentz transforms of static solutions. So there's a further invariance in the nonlinear energy critical nonlinear wave equation, and that's the Lorentz invariance. And the solutions, you take a Q in sigma, that's a non-zero solution of the elliptic problem. You take a direction L, which is strictly less than the speed of light, which we are taking to be 1 here. And then you can manufacture a traveling wave in the direction of L by the Lorentz transform of the static solution. Okay? So this is a traveling wave solution. And as I was saying, when we introduced this method, our ultimate goal was to see if there was some model, at least, in which we could establish Soliton resolution. Okay. So the expectation here, I will now have a precise statement of what we mean by Soliton resolution for type 2 solutions. So remember, type 2 solutions are solutions whose energy norm remains bounded in the interval of existence. Okay. So what we would like to do is that there's a number which counts the traveling waves Qj, which are solutions of the elliptic equation, and directions Lj, which give you, with the Qj, a traveling wave solution. And if you have a sequence of times converging to the final time, which may be finite or infinite, we have scaling factors and translations that are mutually disjoint, and this is coded in this orthogonality condition. We call this the orthogonality of the parameters. And a linear solution, which we call the radiation term, such that along this sequence of times, our solution equals the sum of the modulated solitary waves plus the radiation term plus a term that goes to 0 in the energy norm as n tends to infinity. So this is what this conjecture is in the present example. Okay? And this, of course, is a mathematically precise formulation. So far, this has been proven in the radial case, and also under some small perturbation theory in dimensions 3 and 5. So let me discuss quickly the radial results. Okay? So the first result, the decomposition, was proven for a well-chosen sequence of times that depended how you chose it on the solution, and the general result was proven for any sequence of time. So let me first describe the proof of the last result. And here the key idea was to use what we call the channel of energy method, which we introduced in '09. And this is a method that allows you to measure the ejection of energy as you approach the final time of existence. So what this Soliton resolution, what causes this Soliton resolution, at least people believe that this is the case, is that since you're working on an infinite domain, there's ejection of mass or of energy as you approach the final time, be it finite or infinite, and you take away some energy until you reach a solitary wave. Then you take out that solitary wave, then you eject more energy until you get to the next one, and so on until you exhaust the energy. And this process should end because you have control on the total energy. Okay, so that's the idea. So, but you have to be able to see this ejection of energy. I mean, people see it in experiments, or even numerical or physical experiments, but you have to be able to see it mathematically. And this is one way in which you can see it. The statement, I mean, this is a slightly complicated statement, but it basically says that if you go far out, outside the light cone, there's always some energy left. Unless, in the radial case, unless you are doubling or minus doubling. So that's how you detect this solitons. Because otherwise, there always remains some energy outside a sufficiently wide extension of a light cone. Okay? So let me just tell you what the key tool for proving this is what we call outer energy lower bounds. And this is a linear bound. It's a bound for solutions of the linear wave equation. And really, this bound could have been proved by D'Alembert. I mean, it uses things that D'Alembert knew, and only that. Okay, so the first thing is, let's do it for, of course, let's be in 3 dimensions. And let me consider the Newtonian potential in 3 dimensions and scale it by multiply it by a scalar factor and put 0 as the t derivative. As we know, outside the origin, the Newtonian potential will give you a solution of the wave equation, the linear wave equation. And but this will not have the channel of energy property. You can see that very quickly. So somehow this has to be excluded on any outer energy inequality. But the point of this inequality is that that's the only thing that has to be excluded. So the meaning of this inequality is that if you do the orthogonal projection to the orthogonal complement in this space of the Newtonian potential, then this outer energy inequality is true. And the fact that we're able to go outside the light cone tells us that from the nonlinear equation we can pass to the linear equation because things become small outside. And then we can use perturbative analysis and use finite speed of propagation to keep the equality between the solutions. So this is proven in a paper in '09. And as I said, it's just calculus. Now there's a version of this in the non-radial case that works for odd dimensions. But here we're not allowing to go further out than the light cone. Okay? And it turns out that if you do the limiting argument and the calculations, when you don't go out in the first inequality, the 2 inequalities coincide. The projection gets thrown away. Okay. So let me tell you a little bit about how we use these inequalities. Let's say in the finite time blowup, for the other case is similar. We first consider the weak limit of the solution as t tends to the blowup time, and one can show that this exists. And then we take the linear solution, whose data at time 1 is this weak limit, and this will be the radiation term. And then we look at the nonlinear solution with that data. And because everything is regular for this, this is a nice solution near t equals to 1. So by the properties of the small data Cauchy problem or the small time Cauchy problem, this difference goes to 0 in norm. And the other thing that is easy to see from finite speed of propagation is that there's a clean break. And if you have a solution and you take out this regular part of the solution or radiation term, the support of what's left is contained in an inverted light cone. Okay? And this is a simple step. Once we do that, we take the difference between the two objects and decompose it into blocks. These are nonlinear blocks. What are the nonlinear blocks? Well, technically, they are nonlinear profiles associated to a Bahorij or R profile decomposition. Anyway, so you decompose this into parts, plus a dispersive sequence of errors, which is small, not in the energy space, because that is impossible, but in a weaker norm that is associated with what we call Strickard's estimate. Okay. If one of these blocks is not plus or minus W, this sends energy outside the light cone by the outer energy estimates. But if it sends energy out of the light cone, it contradicts the support in the inverted light cone. And that's how you kill all the profiles that are not plus or minus W. Then you have to show also that the dispersive error is in fact small in energy, and for that you do the same game. You again use this outer energy inequality, and that finishes the argument. Okay? Of course, the argument is not 2 pages long. Okay, there are many technicalities and so on, but I'm trying to explain the core of the argument. Okay? So the argument for a well-chosen sequence of times was different. So this was the first argument where instead where we didn't succeed in proving it for all sequences of times, but we proved it for a well-chosen one. The first step, let's say again in the blowup case, t plus equals to 1, was to show that there can't be self-similar blowup. What does that mean in this context? It means that in the region between two inverted light cones, there can't be any energy, even though you're blowing up. That all the energy is concentrating in a cusp. Okay? So we proved this in the n equals 3 case, again by using this outer energy inequality. Once we had that, we combine this with some identities. These are, for those of you who learned the elliptic theory, and you know this Pohorzaev identity, these are hyperbolic versions of the Pohorzaev identity. And they're called virial identities. And anyway, there are a couple of virial identities that give you, relationships between different terms that appear. 2 star is the exponent that appears in the energy, where if you want to think about n equals to 3, 2 star is 6. Okay, I only think of that case when looking at this. And then there's another one, and this is important that there are 2 of them, and that's because the wave equation has 2 time derivatives, and so there are 2 such identities. And you see that the same ingredients are coming, but the coefficients are different, and one can play that. Okay? So if we add 1/2 times 3 and 4, we see that this term, which is the time derivative squared, is a plane derivative. of some other object. Okay? And there are some small errors, but let's not worry about it. But using the fact that there's no self-similar blow-up and this identity, you can prove that the Cesaro means, as you approach the blow-up time, of the time derivative goes to 0. And that somehow is telling you that in some asymptotic way, you have a static solution. And that's how you extract static solutions. Okay? Time derivative is 0 asymptotically. Okay? So this time you show that the nonlinear blocks are all time independent, and the only radial time independent solution is plus or minus W, and so you identified that. And now, for the dispersive term, you can see that the time derivative is going to 0, and then you now have to show that the spatial derivatives go to 0, and here you have to again use this channel of energy argument. Okay? But here, the weaker one of the two channel of energy arguments suffices. Okay. So in the remainder, I'm going to turn my attention to higher dimensions. The reason I discussed this for n equals 3 was not for simplification, but because at that point, that's what we could show. And I want to explain why in the next few minutes. Okay? But before doing so, I want to mention that the techniques that we just explained have had other applications to other problems, for wave maps, equivariant wave maps, for defocusing energy critical wave equations with a trapping potential. And here there are works of Kott, Lori, Schlag, Liu, Jia, and others, myself there. And at this point, I think I would like to mention a fundamental fact, which was proved with Kott and Schlag. And this is the fact that these outer energy inequalities fail for all even dimensions. It's not that we just couldn't prove them, they're false, even in the radial case. So this came as a surprise and as a blow, because it meant that there was something that we didn't see, right? We didn't see this coming. And now the weaker one of the two survives in dimensions 4, 8, and 12 when the data has 0 time derivative, and in dimensions 6, 10, and 4 when the data doesn't have space derivatives, but not otherwise. Okay? And it's not failure of the method, you can write the counterexample. Okay. So in another work with Lori, Liu, and Schlag, we've shown that these outer energy inequalities in the radial case, the ones where you go outside the light cone, are all true for all odd dimensions, but the projection that you have to take out becomes larger and larger with dimension. It increases as the dimension. The dimension of it increases as the underlying dimension. So this becomes a kind of nightmare in combinatorics to prove this. And there's a universal constant in the bound. The constant is 1/2. It's independent of the dimension. Anyway, we were able to use this to prove a stable Soliton resolution for exterior wave maps on R3. Now, in 14, my PhD student Casey Rodriguez used this analog of 1 for all n to prove the radial case of the Soliton resolution along a well-chosen sequence of times in all odd dimensions, but for a well-chosen sequence of times. Okay. So what do we do for n even in the radial case, and what do we do in the non-radial case. So that's the next part of the tale. I'll start by discussing the four-dimensional case. I know that at first glance this is extremely tedious, right? Why you do one dimension and not another. But it's guided by the math, unfortunately. So everyone has to do it, but you will see the conclusion. The conclusion will be rather interesting in the end. So let's discuss the radial case in 4D, which is very close in spirit to co-rotational wave maps from R2 into the sphere, S2. The first obstacle in trying to do this, even for a sequence of times, is that we do not know that self-similar blowup is ruled out. And this is the first thing to do in order to implement this strategy. Now, why didn't we have this difficulty in the work on corotational wave maps? And that's because there were classical results of Christodoulou, Chatat, Tavildar-Zodé from the 90s, which showed this fact, the lack of self-similar blowup for wave maps by integration by parts. They didn't need exterior energy inequalities, they did it by integration by parts, but crucial was the finiteness of the flux. And this is a consequence of the fact that the energy density is non-negative. And that's one of the differences between wave maps and the semi-linear problem, that in wave maps the energy density is non-negative. And in the semi-linear problem, it's not. Of course, you think that the semi-linear problem is introduced as a model for wave maps, so why should it be worse? Okay, so this had bothered me for a long time. And we will see. What happened is that in the work with Kott, Laurie, and Slag in 14, we reversed the passage between wave maps and semi-linear equations. Instead of using semi-linear equations to study wave maps, we used wave maps to study semi-linear equations. Okay? And this is a simple observation. Suppose you look at a radial solution of the energy critical wave equation in R4, and you consider R times U. And you write the equation that it verifies, it is here, and we let f of c equal c minus c cubed. The important thing is that this constant is 1, so this corresponds to the wave equation in R2. Okay? So you can think of this as a wave map, and this is the nonlinearity of the wave map. Now, if you look at the primitive of this nonlinearity, okay, we can calculate the primitive of this. It's psi squared over 2 times 1 minus psi squared over 2. In the case of wave maps, this nonlinearity is always non-negative. Here, it is not non-negative always, but it is non-negative when this guy is small. Smaller than root 2, right? C smaller than root 2. And this is what we are going to exploit. And you have the conservation of energy for this equation, where this quantity is preserved. And the density of energy, which gives you the flux, is this. And f of c is non-negative under this size condition. Now remember that there is this radiation term, which meant that the support is contained in the inverted light cone. This V is a regular solution, so as you approach the tip of the cone, it has to go to 0. But V equals U on the boundary of the cone. So near the boundary of the cone, U has to be small. And now you revisit the classical arguments of wave maps, and you see that they work provided the cone that you're taking away is close enough to the light cone. But once you get this argument to work, you get that the psi tends to 0 even here, and now you can iterate. And you just iterate this argument. And it thus gives you the lack of self-similar blow-up. Thus we could start this process. And now we use the fact that in R4, the weaker one of the two outer energy inequalities holds if the time data is 0. But as we said, because the DDT was in Cesaro means small, that means that the DDT of the error is small. And therefore we can use that and conclude the proof. Okay? So that's how you do the R4 case. Of course, what do you do in R6? In R6, the good data gets flipped. So it's no longer the one with t derivative 0. So this has to be thrown out the window. This will no longer work. So here, I want to mention some recent work with Howard Jia, who's sitting in this room, hopefully awake because he arrived at 3 in the morning. Anyway, and we proved this result for n equals 6. And in fact, we gave a proof that works in all dimensions for, in the radial case for a sequence of times, and dealt with all equivariant classes for wave maps and for radial Yang-Mills in R4. And the idea of this method was that you could do it without using channels of energy. Okay? So the first step is again to prove lack of self-similar blowup, but the argument that I sketched before works in all dimensions if you weigh things properly. Okay? So then you get that the time derivative in average goes to 0. Now we use the other virial identity, and then you prove that in average this quantity goes to 0. Now at first glance this looks like a useless thing because this is not a coercive term. Okay? You can't extract information. But on static solutions, you've already gotten the decomposition into static solutions plus an error which is small in some weak sense. This quantity is 0 by integration by parts. Okay, that's what the solutions of the static problem do. So for the terms in the decomposition that come from these solutions, this contributes nothing. So you only have the error term. The error term is small in this weaker sense, which in particular implies that the 2-star norm of it goes to 0, because that's a weaker norm. But then for the error that we're trying to show goes to 0, in fact the gradient goes to 0. Because this non-coercive quantity becomes coercive if this goes to 0. And that's how we conclude this proof. So you might call this hocus pocus, but in fact there's a conceptual thing to be learned from this. Okay. So the last 10 minutes of this talk, I'd like to concentrate on the non-radial setting, and first start with work of Howard Jia last summer. And the first thing that Howard did was to extend the analogy with wave maps to the non-radial setting. And he was able to do that and use that to control the flux in the finite time blow-up case. Once he controlled the flux, he found a Morawitz type identity, which is analogous to the wave map Morawitz identity, that allowed to show that the decomposition holds in the non-radial case, in the finite blow-up case, but with the error only tending to 0 in the weaker sense. Okay? So in some sense, this Morawitz identity replaces the fact that the DDT in average goes to 0. And it contains information that allows you to kill off all the profiles that are not Lorentz transforms of static solutions. But you still have this error, and this only works in the finite blow-up case. Now, in order to do this, it was very interesting. He did not use any channel of energies, that he used the idea of combining the virial identities. So this idea of combining virial identities was embedded in this proof. Okay. So in the case when t plus for the infinite time, there's a new difficulty because the extraction of a linear radiation term becomes a very non-trivial thing. Now this was done recently, last fall, in a work with Ducaire and Merrill. It's just posted on the archive. And using that and some new ideas, we were recently able to show, also with Jia, that you have the Soliton resolution in the non-radial case for all type 2 solutions for a well-chosen sequence of times, both in the finite blow-up case and in the infinite time case. And this is true in all dimensions. There's no difference in the dimensions in this proof. And so we start out with a type 2 blow-up solution, a type 2 solution, and we consider the first case, t plus is finite. Then we have to, so you consider the singular set, which is the set where you really cannot extend the solution any further. I won't give the technical thing, but it's like the points in the natural Cauchy horizon. And this is a finite set, and you take a point there. Then there's a number, j star, and this j and j star should be, this one is a type of should have been j star, which is bigger than 1, and a little radius, which is positive, and a radiation term, this regular solution. Then there are scales, which are shrinking faster than self-similar. There are positions, which are all strictly confined in the properly scaled unit ball, and can be obtained in this way. And traveling wave solutions, such that in the small ball, the reason you restrict to the small balls is because you could have different regular singular points, and you just want to be in the neighborhood of 1. Okay? But there's finitely many, so you can always shrink enough so that you're in the neighborhood of 1. So in this ball, you have the decomposition in terms of the radiation term, the modulated solitons, and the error, and the parameters are separated in the usual way. That's the finite time case. In the case, in the infinite time case, this is the result with Ducaire and Merrill, the recent result where we can extract the scattering part of the solution. This is the scattering part of the solution, which away from any translate of the light cone contains all the energy. And then outside from that, you have translations and scalings and Lorentz parameters that give you the direction for the traveling waves and QJs, such that the solution and this well-chosen sequence of times is the linear solution plus the sum of modulated solitons, traveling waves, plus an error that goes to 0 as n goes to infinity. And so the only hypothesis is a type 2 hypothesis that the thing is bounded. Okay, and I think I can conclude with that. Thank you very much. Yes. I think right now we don't really understand well the subcritical case. And the subcritical case is, from the point of view of this approach, it's harder than the critical one because of the scaling not coming in.
Is it harder both in both case 1 and case 2?
Yes.
What about the supercritical case? Is it easier?
The supercritical case is always harder. Yes. Okay, so they're not generic at all. So this is a very interesting question. So for instance, if you look at the solution W, in every neighborhood of W, you can find solutions that blow up in finite time of either type 1 or type 2. And you can find solutions that scatter to linear solutions or scatter to other objects. So, right. So this is a very non-stable picture. But as I was saying before, some of these ideas do apply in stable situations. For instance, in the case of wave maps on R3, in the exterior of a sphere, where you put 0 Dirichlet data, then it's a completely stable situation, and there is a Soliton resolution like this. And recently, my student Casey Rodriguez has been able to prove a similar thing for wormhole spacetime, and this is a completely stable situation.
I'm struck by the fact that you have sequences of times and not continuous. So are
Right.
there counterexamples in which...
So, no. So what I should say, maybe I have another, yes, I have another slide, I think. So what happens is that so this is a very difficult question of time oscillations. How big can time oscillations be? And that is connected to this idea of how do solitons interact with each other. So we're beginning to understand that, but it is extremely complicated and it will take time. No pun intended. Okay. No. This is... Pardon me? For the spherical symmetric in times 3, we have it for all times. But, one interesting thing that's happening here is that the difference there is conceptual in the fact that there's only one solution that's static in the spherical symmetric case. In the other case, there's infinitely many solutions, and there can be some instabilities associated to this solution. And these instabilities could produce surprises, okay, when one understands interactions. And it seems to be a very difficult problem to decide whether those instabilities do exist or not, having to do some difficult spectral theory assumptions. Okay.
All right, we'd like to thank our speaker for a very interesting